Hi everyone, welcome to our final presentation for the project FlightFareFinder, which is finding the cheapest flight to GHC. We'll be using Dijkstra and Bellman-Ford algorithm, and our teammates including Siying, Peng, Zhuoyi, and Anqi, Zhao. We will be briefly introduce the Dijkstra algorithm and also the Bellman-Ford algorithm, which is handling negative edges, and also don't forget to wait for the conclusion by the end. Firstly, I will briefly introduce the GHC, which is stand for the world's largest gathering of women technologies. It will draw thousands of attendees from across the globe. And also, as CS student, attending GHC can be a transformative experience, opening to exciting possibilities in our careers. However, attending GHC becomes significantly expensive, and identify the cheapest flight options become essentials, particularly for students with limits of budgets. So in our case, we're starting with the San Jose campus to the event in Orlando, Florida. Although the direct flight is the shortest distance, in certain cases, flights with layovers can be more economical than nonstop flights due to factors like promotional deals. Airlines may reduce their prices for connecting flights to attract more travelers. To find the most budget-friendly options for attending GHC with fixed dates, we have embarked on a mission to develop an optimal algorithm that enables our students to attend GHC in Orlando. We try to use the Dijkstra algorithm to generate the cheapest way, and then we also apply the special offer case with the Bellman-Ford algorithm. My teammate Zhuoyi will introduce the Dijkstra algorithm next.
Thanks, Anqi. So we learned in this course that a Dijkstra algorithm is to find the shortest path between nodes in a weighted graph. So it's a perfect algorithm for our project to find the cheapest flight from San Jose to Orlando. In this graph, San Jose is our starting point, and Orlando is the destination. The 4 nodes in between are 4 connecting cities, and the numbers on each edge are the cheapest flight price between these cities. You can notice that the nodes in the top left graph are color-coded, and on the top right is a note explaining the color and symbols in the graph. At the bottom, we have a table showing the shortest path to each vertex, which we will update as we traverse the graph. Before we start, the prices are set to infinity since we don't have a path of connecting flight yet. Now let's start from San Jose. The adjacent cities to San Jose are Denver and Chicago. The price from San Jose to Denver is $120, and the price to Chicago is $110, which are both cheaper than infinity. So we'll update the table at the bottom for both Denver and Chicago. Basically, we are doing a breadth-first search, looking for all adjacent cities and update the cost if it's lower than the previous cost. Then we pick the next node with the lowest cost among the unvisited nodes, which is Chicago, and repeat the same process, and it will update the price of Houston to $200. Next, we move to Denver and repeat the process again. This will update the price for Nashville from infinity to $320, but remain unchanged for Houston since it's higher than previous calculated price. Then we just repeat the same process for Houston, which would update the price for Orlando to $300. And also repeat for Nashville, which would make no change to the bottom table. So this graph shows the final route we found using Dijkstra algorithm from San Jose to Orlando with the cheapest flight ticket of $300. This page shows the code implementation of Dijkstra algorithm with some key points annotations. And here's the output of our code, which exactly match the result of the graph we walked through earlier. The complete code can be found in the final project report appendix. We can see that the Dijkstra algorithm is a good solution for our problem to find the cheapest flight from San Jose to Orlando. However, there do exist some limitations for Dijkstra algorithm, which I will pass to my partner Peng to talk about more details.
Thanks, Zhuoyi. And let me present a negative challenge that Dijkstra algorithm faces and reacts. Recently, our team member received an exclusive invitation to the conference in Nashville. It's not just a presentation opportunity. It comes with a sponsored Disney trip and 150 reward. This charming offer transforms the cost of going from Nashville to Orlando. So, completely reshaping our travel cost graph as shows. In this new puzzle, we dive into Dijkstra algorithm. Here is the twist. The algorithm pick up the battle pass with 300, and even though the top route costs just 117, this uncovers a significant reality. Dijkstra algorithm can face challenges when dealing with negative scenarios. Dijkstra algorithm, it thrives on the belief that distances only rise, like stepping stones leading upwards, yet introduce negative edges, and this harmonious climb falters. This is a fundamental cause, which represents in a direct factor that for the current node, calculate distances to unvisited neighbors if shorter. Let's dig into the failure by working through the algorithm step by step. At first, we initialize an array to track the shortest distance from the source node to each other nodes. That means set the distance to the source node as 0 and distances to all other nodes as infinity. And we start from the source node, that's 0, San Jose. So we make our nodes are as unvisited. Okay, and so we stop our iteration 1, we visited node 0 and update node 1 and node 2. So we mark node 0 as visited and choose current node in shortest path from unvisited nodes, serving as for the next iteration. Now that's the node 2, because it's smaller. And then this is the same as the previous general case that Zhuoyi showed. Okay, it remains the same process. And here is the pivotal moment. We step into node 5 Orlando, no updates needed, and Orlando are checked off our list. At this turning point, a dead end greets us. Let's uncover the outcome. Okay, here node 3, Nashville is our next and last stop. But hold on, all other nodes have been visited. Therefore, no node could be updated, although the path is shorter. Then mark node 3 as visited. So our journey reaches its end as every node has been explored. In the grand finale, the curtain falls on our exploration that's missing the shortcut due to no backtracking rule. Remember node 5? That's before the node 3. It's played a role. A snapshot of our journey, twists, turns, and lessons learned. Let me pass it to Siying to show how to handle this challenge.
Okay, thank you, Yue, for the introduction. So in the cases of negative edges, we can use Bellman-Ford algorithm that we learned from our CS5800 classes. It will be able to deal with the graph with negative weights, and let's see how it works. So the crux of the Bellman-Ford algorithm is edge relaxation. Before we dive into that, let's look at some definition. So DI is the cost to get to a vertex I from the source, and the weight of U and V is the cost to go from vertex U to vertex V. And the edge relaxation is saying that we update the cost of vertex V if we find a cheaper path through vertex U. And let's look at this example here. DU is 15 and DV was originally 50. And the cost to go from U to V is 20. So let's calculate the new distance. It's going to be 15 plus 20, that's 25, and less than the original cost of DV. Therefore, we update DV with the newest, cheapest cost, which is 35. And to do the edge relaxation, we're going to do it for V minus 1 times. Why is that? This is because a simple shortest path from the source to any other vertices can have at most V minus 1 edges, which is in the case of complete graphs. And as we can see, Bellman-Ford algorithm focuses more on edges compared to Dijkstra, which focuses more on vertices. And next, let's look at the initiation of the Bellman-Ford algorithm. At first, we will add all the edges to the edge set here. We're gonna iterate them through one by one for v-1 times. And here was initially the distance was set to infinity except for the source node. And this is the edge relaxation steps that we're gonna do. So for the first iteration, let's look at node 0 and node 1. So node 0 costs 0, and then node 1 costs infinity initially. And we're going to calculate the new distance, which is going to be 0 plus 120. That's 120, and it's smaller than infinity. So we'll update the cost of D1 to 120. At the end, for each node, we're going to update the final cost, and you can see here it's all updated. Okay, so after the first relaxation, going to the second one, so we got lucky in this case, convergence is achieved and no changes were made in here. So it remains the same as the cost from the first iteration. And also staying true for third relaxation and fourth. And lastly, we have our final cost after v-1 times iteration, and which match US presentation. The final cost is $170. And it successfully take into account of the negative weights and get the valid solution. So just to sum up the Bellman-Ford algorithm, we start from initializing the graph, initialize the distance to all infinity, and then add the edges to the graph. And we do the edge relaxation for v-1 time, like we shown before, and we return the cost at last. This is the code implementation of Bellman-Ford algorithm. You can see here, initialize the graph, and during the edge relaxation part, the outer loop accounts for the number of vertices. We're going to do it for v-1 times. And in the inner loop, we're going to update the cost for each edges. At the end, we return and we plug in the case of our problem, which is find the cheapest path, and we have successfully identified one. Even though our Bellman-Ford algorithm successfully identified the correct cost, it still has some limitation. For example, for the normal form of Bellman-Ford algorithm, the time complexity is big O of VE, which accounts for the two nested loop, the number of edges and number of vertices. But in the case of complete graph, where each vertex is connected to all vertices in the graph, the number of edges will be equal to n times n-1 divided by 2, and plug this one back in here. We got big O of n cubed for a complete graph. So which is kind of expensive for time compared to Dijkstra algorithm. And the other limitation is redundant iterations. Like in our case, we reached the convergence for the first iteration, the rest remaining redundant. And lastly, it's gonna fail on negative cycle because it will keep updating itself and go into an infinite loop. So for this project, we have found the cheapest path from San Jose to GHC. And to apply this algorithm to a broader scenario, we can use it to find the cheapest path for international flight where there will be more intermediate stops. And it can also be used in navigation systems like Google Maps and social media network like Facebook. And that's all for our presentation, and thank you for listening.